Great. Here we are. So, for better or worse, this will probably be a little different than what we've done. We'll probably have a little more application and background, less coding. We will get some. We will get a little bit of some code, but yeah, I was going to kind of just talk a little bit about how we use Python where I work. I work for a company called BMT, British Maritime Technologies, but the product I work on a product called TUFLOW, which is an engine for simulating floods. So we'll look at that and talk about what that means. But that's what we're doing. So we'll get in. So flood modeling background, also known as what is TUFLOW. So we'll kind of give a little bit of a background on kind of what I do and how this kind of industry works. Kind of center around our product. Our product's called TUFLOW. There's other ones out there that people use, and they'll use Python as well, more or less the same ways often. So TUFLOW, it's a physics-based model, right? So model's a word that gets thrown out a lot for lots of different things, but it's an engine that is doing physics calculations, right? And so we're going to run simulations and predict where the flow of water, sometimes sand or other particles along with the water, but principally the water, figure out where it's going, how deep it's going to get, are you going to flood your house, those kinds of questions, right? We'll show a few example applications. So we talk about kind of a physics-based model or engine. These words kind of get interchanged a little bit. And basically what it kind of boils down to, I had Gemini help me with this graphic. It's pretty good. But anyway, you've got some kind of a system, right? And within that system, you're going to use math and equations to try to figure out how things work in that system, to try to tell you kind of what's going to happen. And every system's going to have some kind of a boundary, right? You're going to have a boundary, and along that boundary, you have to kind of tell it what's happening, right? So in our case, we've got, a model. We're looking at maybe the Des Moines area or something. And so you're going to say, well, what's happening in the area? Well, you've got some things on the downstream end. It's not very exciting here in Des Moines, but you'll have rainfall that's coming in. You might have wind. Wind's probably not going to be a big deal here. And so you're going to kind of look at it different places, different ways, right? So if we were looking at Hawaii, all of a sudden what's happening downstream is the oceans going up and down and things like that. So it gets a little bit different. Wind makes a much bigger difference in places like that. But this is what we're talking about. There's some kind of a system that we're trying to represent. And so in our case, some of the inputs that we're looking at is, well, we need to know what the elevations are. This comes in what we call a DEM usually, digital elevation model, right? If you zoom around Google Earth, this is kind of what you're looking at. We're going to have rainfall data, right? So that can vary through time. It can vary space. So you can have grids that are involved, or you can do something simplified for that. You're going to have whatever downstream water you're working with. It's going to get involved. You might have some bridges or other structures, right? Bridges have these piers that go down into the water. They're going to break up the water, change how it works. Bridges are often one of the things that we're interested in what's happening right there at the bridge. One of the most common reason bridges fail is because the water erodes away the piers, erodes the foundation. I think it's 95% of bridge failures because the water eroded. So you have to predict, well, how far is it going to erode and make your bridges deeper.
Now, the
Sorry, come.
Do they always come out at the bottom? Is the bottom eroding?
Yeah, it's usually right around the piers. The water speeds up as it goes through the bridge. It increases how much the sand gets picked up, and then it also right around the piers creates these helical motions. And so they have these equations and they run these models to try to predict how far it goes down. And it's really interesting because then it's, especially big rivers like the Mississippi and things like that, they'll have a flood come through and it'll erode down and then it'll fill back up. So if you go in back even after the flood, you'll say, oh, it didn't even get close to eroding to the bottom, but it might have. It just filled back up before you came back. But yeah. So we might, if we're looking at designing an urban area, we might have pipe networks that we're looking at. Those are going to be inputs. We might have different configurations if we're looking at different designs there. And then we're going to have outputs, right? So our outputs are going to be water levels, right? We're going to see where the water is at every kind of point in our domain. We're going to have velocity information, right? Sometimes we're really worried about water levels, sometimes velocities, and sometimes it's the combination. Here in the U.S., we don't do it as much, but our software is used all around the world. Most of the people I work with, in fact, I'm the only person in North America that I work with, but of all the people that are on the team. But so around the world, they're really big on these hazard levels. So they'll look at velocities and depths together. So it's not just whether or not the water gets 4 feet high. It's, well, if it gets 4 feet high and is really moving fast, it's really dangerous, even though it's, might be more dangerous than 6 feet and slow. And so they look at hazard levels in addition to just water levels. And then discharge is just how much water is kind of going past. So this is kind of the inputs and outputs in our system. These are the equations. I'm not going to break this all down entirely, but the things that we're mostly solving inside of that system, again, that we're representing are these equations. It can get a little bit different when you have pipes and things, but basically the first equation is that we have to have a balance of mass. Any water that comes in is going to change how much water is in the system or in a cell in the system. And so it's going to go up or down depending on what's happening within it. And then this is the momentum equations. And so it's like what are the forces that are being applied, and those forces, the momentum caused by those forces has to balance. And so these are things like gravity is a big one, right? So if it's steep, gravity is going to be pulling harder on it. You got the friction across the bed. You have turbulence where water's colliding with other particles of water and creating heat, basically. You're losing energy based on heat. And so this is the momentum, and is closely related to energy. It's that we're solving to try to kind of keep a balance there. And so these equations work together to try to predict how water is going to move through a system. So let's look at some examples. What kind of we see kind of for output? What are some of the applications that we're looking at here? So see if I can get this to play. So this is an example. I think most of these are going to be Australia. This is somewhere in Australia. They get really big floods there. And so this is an example of a simulation. Mostly water coming from upstream, I think, on this one. And just kind of looking to see what happens. Next, maybe. Yeah, when you get used to a certain orientation, whether you're, wherever you're kind of used to, it's really hard once you start seeing it. And it can flow all different directions depending where you're at. So this is an urban example. So we have rainfall that's just landing right onto the domain itself. It puddles. These little red parts are pipes, so that some of it will make it to the pipes and come out and end up down in the ocean or these rivers on the edge. And so we can just kind of look and see. And usually when they're looking at something like this, they're looking to say, well, what can we do to make it better? You know, can we add some detention? Can we have bigger pipes? What are things that we can do? And so we can run kind of a pre and post and say, well, it changes this way or that way. So this is kind of a lab scale view of kind of what would happen in kind of a dam break scenario. So they have all this water kind of stored up here, and then they raise the gate and let all the water come flying through, and it hits that concrete block to kind of represent a building. And so this is an example of kind of a dam break kind of an exercise. I've done real dam break models, kind of similar way, but this one's kind of fun because you really get to see kind of the interactions of things, how it hits the building and starts to pile up, and you kind of see there's kind of a face there. It gets kind of steep, and it's getting a little more shallow as time goes on, but it moves around a little bit. So it's really interesting to just kind of see what's happening in the simulation on this one.
Question on this.
Yeah.
First of all, what scale are you at? Like your feet, tens of meters, tens of...
This is,
How fine?
this was I think this was done in England, but this is probably a flume that's, I think it's like 20 feet long or something.
And then if you zoom
But
in, like how detailed of predictions are you making? Are you making predictions
in this case, they're really small cells. And so, yeah, I didn't really get into that, but different model, or when you're doing different models like this, you'll kind of break it up into these cells. We have two products, one that does it all in a grid style, but then you can have kind of grids that are inside of grids to make some refinement. And then we have one that's really flexible that everywhere is different. If you've used tins before, it's kind of like a tin. And so depending on your application and where you're at, so in that one, they'll use it in coastal areas a lot. In the deep ocean, they'll have really big, kilometers, big cells. And then as they get up close, then they might have on the order of meters or small. In this case, it's like centimeters. But usually we don't do that kind of scale for a real life model. And so it kind of depends on what you're looking at, on how big that is.
And then for this model running, is it set up such that you can take that building right there and just move it within the model and it'll all recalculate the flows? Or is that like starting all over the whole new process to try and recalculate the flows if you move that building?
We have some pretty easy tools to move those things around.
Yeah. And it just goes on that.
And then you tell it to run. It's kind of we go run it and then we go analyze it as a second step. So we kind of start over on the process. But I didn't do this one, but a lot of them will run in a few minutes. I worked on a really big model in California that had the floods kind of go around Sacramento. When they have really big floods in Sacramento, the river through town isn't big enough for it. So they've bought all this land west of town, and they'll send the flood off around it, and it's got like a duck hunting club and some nature and some farms. Anyway, so that one would take about 24 hours, but we would simulate from like October through June. So it was a pretty intense model. But yeah, most of them are running in minutes to hours. Every once in a while, somebody will get something running really crazy, and it'll take a day. for a few days. Now we do, most of our stuff is 2D. They have these CFD models, and they'll run those for like a month and stuff, really crazy stuff. But it all just depends on what you're interested in and stuff. So this is a simulation of a cyclone. I think they call them cyclones if they're in southern hemisphere, and we call them hurricanes in the northern. And what we're looking at on this top part is actually the water level. And so is right where the eye of the hurricane is, or cyclone, the water level actually goes up where it has that negative pressure. And so it follows it through, and then I'll see if I can kind of stop it at the key part here. So it's moving along, and then as it gets close to shore, okay, there's pretty good. As it gets close to shore, you see that rise up. Now this is super exaggerated, but that's kind of the effect that's happening. What happens is the wind is, creating this big surge, and it's pushing the water up closer. But when it's out in the deep ocean, it doesn't have anything to kind of slow it down and make it rise up. But as it gets close to the shore, that friction makes it so that it pushes it up. So we do have, we can use it for hurricanes. And then this one, we're going to have a little bit of, this is kind of a coastal area. You'll see the currents going up and down, but this little spot here that kind of goes and moves around, this is to simulate like a pollutant. So you had some kind of a spill or something in there, and it's moving through, right? That's another application, is water quality and kind of seeing how that moves through the system.
So in that case, are you dealing with different densities of liquid and treating that differently, or is it?
Yeah. So yeah, we'll be doing, a lot of times that'll be 3D, and if you're close to the ocean, you have to worry about salinity and temperature, and they're different vertically and they're different spatially, and that all has an impact on how it moves and moves through the system. So, but yeah, so you have to do 3D to get all of those, and it's a pretty involved project to get some of those ones. They're pretty too. So we talked a little bit about what the applications, and so TUFLOW, I'm talking about, it's kind of like it's command line interface, right? It's a pretty old school, you pull up the command prompt and run it. And we have a bunch of files that we feed it in, and it'll spit files out. And so we start with these text files, and these actually kind of look like programming. We'll look at one in a little bit, but we have these text files that are going to kind of control what goes into our simulation, and the other kinds of data that we're going to feed in. We also feed it in things like CSV files, right? So that's going to be like the tides come in, CSV files. Rainfall can be CSV sometimes. And then we also have GIS data. It's basically geography data, right? So it can be rasters, so that can be like an image with elevations. So like, back to Google Earth, right? When you're flying around and seeing the elevations, that's kind of a raster that they've got behind the scenes that they're using for elevations. And then you can also have what we call vector data, which is points, lines, or polygons, and then it can have different attributes. So you have these tables based on that, and that's what we usually work with inside of GIS, and that's kind of how people often set up our software. And we also have some specialized output files for the results. But we try to have our stuff pretty flexible and with open formats as much as we can. So the solvers, we kind of have kind of the old school and newer ones. And our old ones, originally, they're all written in Fortran. Still a lot of Fortran code out there. Yeah, good old Fortran. And then some of our newer stuff with C and C++, and uses the NVIDIA CUDA to crunch numbers. These kids playing computer games in their basements they figured out they needed crunch all these numbers to be able to play video games, and then scientists figured out, wait, we can use those to crunch numbers for other things. And so yeah, those graphics cards, they're handy. They really crunch numbers. So that's where a lot of our new stuff is. And so why am I, if our stuff's all Fortran and C++, why am I here talking about talking about Python? Well, we use Python quite a bit in the data preparation side, and we're going to kind of talk some examples of each of these. On the preparation side, we'll use it, help gather data. A lot of the data out there is accessible by API. You can get it through Python. We use it when we're building models. All that GIS data that we talk about and manipulate, that's all available with tools with Python. We do it when we're running simulations. We have a little runner I'll show you that we use it to manage those running simulations. And then when simulations are done, we need to be able to look at that information. We saw some of those animations. We'll look at how that comes together. And then also data analysis. We'll use Python for all of those pieces. On the data analysis side, once I worked on that big project I was talking about in Sacramento, they had all these landowners inside, and they wanted to give them information about everything that was happening on their property. Well, part of their property might flood, and they had like 5 different alternatives, and they wanted to tell them, how the different alternatives affected them and things. And it was just, we ended up giving like this huge PDF of all these tables of everybody's property. Well, about 30% of the time it's going to be 15 centimeters deeper, or some amount of more depth. But it's really, it was so variable that it was really hard to kind of summarize. But that's the kind of thing that I spent quite a while just trying to get all that numbers out of, using Python to crunch all those numbers. Now we kind of have 2 kinds of users. We have the developers, and we have the people that are out there using it. And so right now I'm a developer. I'm working on these tools for modelers. And my background, I started as a developer, and I was doing kind of the front-end stuff. I worked for a company that was doing kind of the graphical side, mostly in C++. Then I went and I was a modeler, working as an engineer here in Des Moines for 10 years. And so then I was using the tools, and that's when I taught myself Python, was actually in that portion. I'd done C++ and Pascal and some other things before, and then I taught myself Python while I was doing modeling. And now I'm back to being a developer, and I'm working on the engine, or the company that does mostly the engine side. But we do develop some tools, and a lot of the tools that we develop are in Python to try to give our users a hand. So I'm going to kind of talk a little bit about some of the things that we talk about and do. Can either be developers creating tools that'll be used by the end modelers, or it could be modelers using Python to help automate and get their stuff done. So we have these, one of our big things that we have is a GIS plugin. GIS is the application software where you work with geographic data. We have a custom plugin. It's got a lot of tools and things in there, and so that's kind of a Python tool, or a Python application that gets used a lot in this process. We'll talk about it. And we have some other libraries that go along with that. We have some Jupyter Notebook tools people could use, and then of course anybody can just pull out some of the core packages and work with them as well. So those are all places we use Python. Some of the key libraries that we're working with, NumPy, Pandas. I'm assuming everybody's worked with those. They're the number crunching core of everything. And then you get to the geospace, and you have things like Xarray, which is kind of like NumPy, or is built on NumPy, and works with specific kinds of raster formats and things like that. We'll show what that looks like. And then GeoPandas is just the geography part of Pandas, putting spatial information on those tables. And whatever plotting library you like, there's lots of those out there. So our GIS plugin, this one's built on QGIS. We have fewer tools available for a product called ArcGIS, but QGIS is a pretty popular open source application that our users use a lot. So pre-processing, they're going to use the plugin a lot. That's kind of where most of our users are working to set up their models. And I talked about how that was all written in Python. And some of those tools that inside of that GIS, they can also access from scripts. We have a library we call TUFLOW, which is a way to kind of help automate setting up these files. Like I said, these control files, they look like code. We've got if statements and variables and all kinds of stuff in there, but they just kind of control how the simulation's going to get put together. And we can set different settings and things like that in there. Like I say, we have if statements. They reference other files. And I know everybody's thinking right now, please show me some code. All right, we're here, Python, and soon, we're going to get there. Before we get to some real code, this is what a control file looks like. All right, so most of the lines kind of have a command and a double equals and then a value and then comments. And so this is how we put together those simulations, and then is just being able to define this information. And some people think this is pretty backwards, that we're pretty out of date because we don't have a fancy GUI. We kind of have a fancy GUI with the plugin, but there's a lot of power actually. It's kind of like, there's tools out there that you can kind of do code from dragging things around and stuff, but sometimes they're not quite as powerful. And that's kind of what we think we get some advantages from people being able to work over here as well. But, oh no, you can't hardly read this. I don't know why it's coming in so blurry, but this is where I was finally going to show some code. So this is our TUFLOW library, and you reference a file that's going to bring everything in. And what we're doing is we're actually bringing in boundary conditions. And I wish I knew why that doesn't come through, but we're just bringing in a curve, and we can plot it and see and do modifications all with this kind of tool that just kind of helps expose some of those in a friendly manner. So whole bunches of things we can do there. We have a series of tools we call that are the coastal modeling GET tools. So we have a GET tide, a GET atmosphere, and a GET ocean. So GET tide, and we're going to have some boundaries. Again, this is part in the middle, that's our system. We have to say, well, we're going to simulate what's happening inside. We have to tell what's happening on the boundary. So we have two boundaries there where the water is going to be going up and down. And so we can get the tides for those with this tool, right? Oh, look, some more code. And so you put in information about like your starting dates, your end dates. The shapefile is given it where the locations are. And you call this function, and it's going to spit out something like this, right? The water's going up and down, but it's not completely symmetric, right? It varies. The tides kind of follow long-term cycles, but they're not just really simple up and down, right? So you have to know when and where those are happening. So this is for the tides. We also can get ocean temperatures and salinity, and those vary both across the space and depth and stuff like that. But they have those tools to try to help gather that information. Then we go to run simulations. This is a little Python I wrote a couple years ago, and I was watching football and needed something to work on while I was watching football, so I wrote this little application, and it's pretty simple. It's just running on the local machine. We're not doing it doesn't go and farm it out to multiple machines or anything, but it just, you can have a queue and you can move them up and down and manage your simulations that you're running. And so that's another place that we get Python in there. And then finally on the output side, when we go to do some of that, and we'll walk through a little bit of this here in a minute. But all right, so we've got, in this case, some kind of a river system. We're going to draw a line along it. So this is our QGIS plugin, all written in Python. Draws the line to create, this is what we call a curtain plot. So this is kind of looking at side view of what's happening along that line. I think we're looking at salinity, so you can see the salinity kind of moving up and downstream based on the tidal action there. TUFLOW again, so we talked about that as a data prep tool. It also has a bunch of tools to help us visualize results. And I'm not going to show that. Then we have a toolbox that we can go look at things. So if we're looking at water levels across the tidal, kind of a tidally driven area, we see the water bouncing up and down. Curtain plots, just like we showed, that these are different ones, right? So salinity, temperature, and this is currents, and so you can kind of see what's happening all across the model and even within sections. And then you can kind of combine them. So this is all different ways to look at salinity. So you're looking at the top left here, this is what we call depth average. So it's just kind of looking at, it's taking all that vertical information and just averaging it. And so you can kind of see on average where it's high or low spatially. The curtain plot we've talked a little bit about, that's looking along a line, what's happening on the Z direction. And then this is at a point, kind of what's happening vertically and then through time. And so there's just all these different ways to try to kind of make sense out of all this data that we're pulling out. And then you can have particles, right? So these might represent pollution. They can, anything kind of goes along with the water. We can kind of have a particle that goes along with it. And then the particles actually sometimes can move themselves. We had a group that was using this to try to optimize like a shrimp operation, like a aquaculture. And so they could actually kind of program these shrimp that when they're in the water column, they kind of swim, and as they hit the ground, they'll kind of go along they'll just walk along the ground, and they would kind of try to optimize it in terms of if the water was too clear, they didn't want to get too high in the water column because they'd be afraid of a bird coming and seeing them, and so they're kind of trying to optimize, how much light that they got, and make sure that the water quality is good for the food, and try to kind of maximize all these different things. And so that was an interesting one because the particles weren't just flowing along. They could actually kind of seek out certain things.
We've got a question from the live stream.
Oh, yeah.
Someone wants to know, is this created using the matplot library?
So, so this animation is definitely a matplotlib graphic, and so a lot of our tools, you know, I talk about, when I showed this one up, right, I talk about this as a tool that we have, but this is built on other tools, like this is built on matplotlib. You know, a lot of these tools are built on other building blocks, and that's what we were gonna kind of get into. But yeah, that one's definitely a matplotlib graphic. Of course, there's a few of them out there. So that's the presentation part, and then I was gonna, if I can work this, I was gonna kind of, it's so hard to read. Let's see. Maybe. Trying to see if I can get it a little bigger, and maybe that'll make it a little easier to read. Might be all we get. Okay. So I was just going to kind of show just a couple little things here. I got a little bit of a cheat sheet, so if I forget. But one of the core libraries that we mentioned, you know, we've got these tools that are kind of built on these, but I thought, well, you guys are probably never going to run into those. So I'm just going to do a little bit of demo and talk through what happens at the core library level, because those are ones that you might run into and might use. And so this X-array, this becomes kind of a key building block for a lot of tools that are going to be working with raster type data. And I'm going to be doing it here in this this Python notebook. And so I've got this up here, and we'll use IPy widgets to do some interactive stuff. And so I just created those libraries, and I've kind of set up ahead of time a reference to this netcdf file. So there's our netcdf file. So now I need to load that netcdf file with Xarray. And so I'm going to create a thing I'm going to call a data set, dset, and it's going to be a Xarray load data set. Look at that. netcdf file. And then we'll look at what's in that data set. So this is a little simulation. It's a pretty small little simulation. We'll kind of see what it looks like here in a minute. But for now, what we know is it has 37 times a grid of 2,000 by 2,000 apparently. And you can't read it very well, but it says there's a water level, there's a depth in there, there's a maximum water level, maximum depth, and then the time when that maximum water level hit. And so this tells us a little bit about this information that we've got in here. And then we're going to look at the max depth first. It's easy because it doesn't have any times to worry about. And so I'm just going to say, give me the dset max depth and show me what that looks like. So if I run this, it says, you know, it's an array. It's got a bunch of not of numbers in there because that's the areas that are dry, right? But it's got some kind of a shape here, this big array. And so now we need to add add some code, and let's see what it looks like. So it's actually really easy. I'm just going to say max depth dot plot, and this is using matplotlib again with X-array. And so what we've got is water coming in down here. We do have some rainfall. There's kind of a little fake town in here. This is kind of a faked data set, if you will. Well, it's not a true location, but it's one that we kind of set up to use for kind of ease and training because it's nice and small. But anyway, so the water comes in here and flows north. And hard as that might be for us, that's how it goes. And so we might want to change some of that colors and stuff. So I'm going to make this aspect equals 1. It's going to make it kind of look more square. Set the size. And see how it's all smooth? Instead of making it all smooth, I'm going to make it so there's kind of distinct levels. We'll see what that looks like in a minute. And then I'm going to change the colors. And then hopefully, if I type this right, see, so now instead, I'm going light to dark blue, right? So all of this is very customizable. It's just that matplotlib figure down below, and you can customize it to show what you want. And so, yeah, the max depth, that's interesting, but what if we want to look at what's happening through time? Well, I'm going to make a little function where I'm going to plot at a time index. So we knew we had 37 of them. We saw that before. And we can come in here and say, I'm going to take the depth data set, and I'm going to select at an index. So I'm going to say time equals that index. Oops. And then I'm going to say plot. And I'm going to do all the same sizes and colors that I did up here. This might be too big though. Maybe I'll make it a little smaller. And so we've defined a function here. And so we can say, well, show me what's happening kind of in the middle, 15. So that's what's happening. Up here we see the time. So this is January 1st, 1:15 a.m. We started at just midnight. In this case, it didn't really matter. And so, okay, so that's what it looks like at one specific time. And what if we want to be able to kind of look? Be handier if we had like a slider. So let's do a slider, right? So we're going to use the IPy widgets here and create an int slider. So we'll go from time or index 0, if I can type, to a maximum length dset time -1. Now, I could have just typed in 37, but then if I wanted to go look at a different file, I'd have to go type that. This way, I could keep it. Start at 0, and I'm going to make the orientation. Whoa. Orientation. horizontal, and readout equals true. And it will do interact. Plot the time slice, and the index is going to equal to my time slider. Oops. Didn't want to do that. Uh-oh. Still got something wrong. What is it? Is it that? No. What am I doing here? Somewhere. I'm doing something wrong. The orientation is expecting me to spell it right, which is not a very good assumption. Hey, so it's blank. Well, there's no rain yet. We haven't flooded yet, so we can, I don't know why it jumps. Sometimes it jumps. So we can kind of just pick an index and see what's happening. Right, and it'll update this time up here. Now, we can also take that and make a little play thing instead. And so we don't need an orientation anymore. Still need a min and a max. Don't need this readout. But I do need a step, an interval, which is going to be a millisecond, so I'm going to switch things every 1 second. And we can come in here and push play, and we can start seeing that flood starting to come up high, start to see it kind of filling in and headed north. What I think is really cool about this is that, you know, this is just our standard output file and this Python library that, you know, that knows how to read them. You know, we're writing kind of a standard NetCDF raster format, this X-ray thing. So it's just a really generic tool. We can just come in there and start building things. And it's pretty cool that those things are out there. So that's all. That's kind of on that raster side. Well, I wanted to show a little bit. So the things that are really key for a lot of our Python stuff is this geographic data. And so this is on the image side, the raster side. X-ray is a great tool there. If you guys have used Pandas before, we're going to look at GeoPandas if I can find it. So in this case, I've got this import GeoPandas as GPD, and we're going to look at the pipe outputs, right? So for a storm drain network like we would have out in the street here, right? You've got pipes. When it rains, the water goes into the pipes through an inlet, and it'll go, and they'll take it to the river and dump it in the river. And, you know, but you might want to know information about, you know, what's happening in those pipes, and you know, if we change those configurations, what's going to happen. And so this file that we've got here is a geopackage file, which is just a way to store points, lines, and polygons in there. And we're going to look at these pipe information a little bit with this tool here. So first off, I'm just going to list the layers that are inside of this file. So this file has a few layers, and the ones that we're interested in is this one is the time series stuff that's happening at a point, and this is what's happening on the line. So this is at the ends of the pipe. This is where we track water levels and stuff, and this is where the inlets would be, and then this is what's happening in the middle of the pipes. This is the same exact problem that we were looking at from a raster point of view. And so I'm going to create a geodata frame for the pipes. I'm going to read the file, and I'm going to give it this layer name. And again, I'm making that generic so I could go in and look at something else with the same notebook if I needed to. All right, so this is just going to be a big table at this point, right? And so it knows information, right? Each of these pipes has an ID. What kind of type is it? Some things that are interesting, like the shape, right? So some of them are rectangle, some of them are circular. Elevation information, and time. So we actually have a line for each pipe and each time, and then it's got some more information over here, like, well, was there water flowing through it at that time? And what we're going to look at a little bit is capacity. So capacity is, well, how full is the pipe, right? So we've got like 3,000 rows there. Time you add up the different times and different pipes. So let's kind of look and see. We're going to look at see what's happening at the maximums. So we'll just do pipe maxes equals. So this is just a command dissolve by ID. So we're going to take all the ones with the same ID, same location, and we're going to do aggregate on a max. I wish this was easier to read. But then we'll just take that and you can look at the head. All right, so now we kind of have a subset. We took the maximums, and I can't see over to it, but there is a capacity there. So probably should have fewer, but we can see where these pipes are by just telling it to plot. And once again, another matplotlib figure. They're everywhere. Right, so you have a couple of little culverts here that go through roadways, and then this is kind of a storm drain network. Like there's a little fictional town here. It's got just a handful of streets, and it's got water that gets collected and gets carried down. So that's where it exists. And so what we want to look at, though, is we want to see where's the capacity getting used up, right? Which pipes are full, because those are the areas that we want to improve. So I'm just going to say, I'm going to plot column equals channel capacity. Now we're going to give it some color. Okay, so we can see that the ones with culverts, there's not a ton we can do there. We might be able to get more water past it quicker. But then we see there's kind of a pipe here that's a little bit higher. These ones that are blue, might not be a lot we can do there. But we want to know where this one is. And so we can go through and have it label those pipes. So now this one's a lot of typing. I'm gonna cheat. I'm just gonna tell you that this pipe that we're curious about is pipe 14, right? So we'll go back to the original data, and we're gonna pull out the data just for pipe 14. So it's just amazing just how you can kind of just pull out exactly whatever kind of data you're interested in and do all these kinds of analysis. Again, this is just the file format that we write and that this tool is using, which we don't. Right, so I'm pulling out just the ones for pipe 14. So this is just what's happening at each time from pipe 14, right? So we can look at that, and we could plot that, right? We can just say pipe. What's happening with the channel capacity here? We saw that it was higher, but what is it doing through time? So we can grab the channel capacity through time from that table we just created and plot it. So, right, for beginning it's not full, gets, basically 70% full, and then back down. So if we added more capacity, maybe we could get the water off there quicker or something like that, right? Those are the kinds of things that we would be looking at. So
In implementation for this, is this like a bunch of sensors on a system of pipes, sends a bunch of readings back, and then that's what you're
well, we're just doing simulations. So we're going to calculate what's happening based on fictional rainfall.
you're given an arrangement of pipes with their sizes and depths and whatever, and then from there you simulate how the flow is going to go.
Yeah, exactly.
And
And
so these tend to be like one-off projects and not like an ongoing monitoring.
so there can be both, and it depends a little bit on where you're at and things. A lot of times cities will kind of have their master model, and they'll add to it and work with it. And so if somebody needs to do work, they'll go pull out the model and do something to simulate and see how it works. They do have sensors, and that we'll use those to try to calibrate, make sure that our model's making sense, because there's things you can change there too. But.
So like, is it capable of taking data and going backwards and creating equations that happen?
No, we don't. But we'll use the outputs to try to change how we'll say, well, it's really not as rough as we think it is, or there'll be adjustments that we will make. Yeah. Yeah, so some of those would be tricky, huh? But yeah, you never know what's going to. Yeah. Sure. Yeah. Yeah, that would be interesting. But so that was kind of what I had. I know it was kind of all over the place with trying to give a broad background and a little bit of the tools that kind of get involved. But is there any other questions on any of it? Yeah.
I was curious about the file format of that big file region where you use like double equals a lot.
Oh, yeah.
What do you call that?
It's just it's our own TUFLOW format. It's specifically for our own engine.
Like, were there other formats that considered there? Is there a long history of using that, or is there an advantage to that specific style, or like, why did you settle on that?
Yeah, I mean, that was way before my time, but that it came about. I've thought about what other ones would be useful. That one's it's an interesting one because it references other files in interesting ways, and it kind of sets things. But yeah, if we were going to do it, if we were going to start over, would it make more sense to do a YAML or a JSON or something, right? There's probably some thing that you could build on that could kind of save some time, but I'm not sure what it would be. We'd have to think through it, but it's definitely kind of a homegrown thing, and this was started. Well, some of our stuff kind of goes back to like the 70s, and then a lot of that format I think was developed in the 1990s. So some of those other formats weren't a lot of the formats that are popular now weren't around then. But the kind of the original author, kind of, who's a programmer, and it kind of was like, I want to kind of make something that kind of reminds me of programming. So that's kind of how he got started. But because he calls it programming a model, it's kind of how he thinks about building these simulations. But, all right. Well, I think we don't have any more questions. So appreciate everyone coming.